In this video, what we're going to do is I'm going to go over the whole RSA cryptography thing that we studied, and for that we use several modules. I have given this spreadsheet to you, but what this video is going to try to do is try to go through what is done in each part of the video. So if you recall, what we do for RSA cryptography is we start with two primes, so the prime P and prime Q. So I have just chosen two primes here. You could change these primes to anything else you like. You have access to web pages that will give you a list of primes, so you can change this to anything you like as long as they're primes. The next thing that we're going to do is we're going to compute the value of n. So if you look at this, it will say that n is the product of P and Q. So that's basically what is happening over here. N is the product of P times Q. Note that the second step we are going to do is to compute phi of n. So phi of n are the numbers that are relatively prime to n. Oops, sorry about that, right here. And if you look at what this is doing, it is computing P minus 1 times Q minus 1. So it is P minus 1 times Q minus 1. Now the reason for this should be something you have seen in the module already. Excuse me, just a little bit of technical difficulty. Another thing I want to mention about this whole file is that, another thing I want to mention is that the cells that are colored like this, these are places where you can enter any input you like. There are some restrictions on what input you can add, but I'm not going to go through those right now. So for example, for P and Q, those numbers have to be prime. E is going to be your public key. So in this case, I have selected it to be 17. So if you recall, we needed to make sure that the value of E is relatively prime to phi of n. So phi of n here is 4240. So we needed something that is relatively prime to 4240. Now, if you observe, this spreadsheet has 5 sheets in here. The first one we went over right now, which is choose primes. Here we selected 2 primes, we calculated n, calculated phi of n, and we selected E. The next part, the next module is going to go over how do you find private key. So the way we find the private key is we are going to start with the 2 numbers that we have. So this number, if you observe, we are getting it to be the public key. This is what we are going to get as the value of phi of n. Now what we want to find is the value of s and t such that s times x plus y times t is equal to GCD of the 2 numbers that we have chosen. So the 2 numbers that we have is 17 and 4240. We are going to find the GCD, and in the process, we're going to find the Bezoid coefficients, one of which will play the role of the private key. So let's first look at how we are going to do. We are going to do this by Euclid's method. So first I have 17, 4240. So those are the numbers that I entered. If you look at the spreadsheet rules, you will see that I'm simply copying it from there. I'm finding the quotient. I'm finding the remainder, And now my job is to write this remainder in terms of the original numbers, which is x and y. So in this case, the value of s is 1, the value of t is 0, and I want to look at how I'm finding these numbers. First observation I want to make is the fact that remainder is 17 and quotient is 0 means that 17 is equal to 4240 times 0 plus 17, this line over here. Now we want to write the remainder in terms of the original number. So we wrote 17 is equal to 17 minus 0 times 4240. So the multiplier of 17 happens to be 1. The multiplier of 4240 happens to be 0. And that's exactly what we have calculated. You can look up the spreadsheet to see exactly how the formula are working, but that's what we are doing today. The last column that I have is basically computing x times s plus y times t, and it should match the remainder at this stage, and it does. And so I have a little bit of check here to make sure that my spreadsheet is doing things correctly. I have a little bit of check there. Okay, so let's go ahead. So the next what we're going to do is we're going to start with the numbers here, which is 4240 and 17. Normally, we would have avoided this step if we were going to do this work by hand, but because of the way the spreadsheet is written, we started first with 17 as the first number and 4240 as the second one. But anyway, so the next thing that we have is 4240, 17. The quotient is 249. The remainder is 7. So the meaning of this line is 4240 is 17 times 249 plus 7. So that's the meaning of the whole idea of the quotient and remainder. We're going to write the remainder in terms of the original numbers. So we have 4240 minus 249 times 17. So the number that multiplied 17 is minus 249. The number that multiplied 4240 is 1. And now again, I have a little bit of check here saying that if this is the value of s minus 249, the value of t is 1. Is the remainder in fact expressed correctly in terms of x times s plus y times t? This would be a good time to actually pause the video to make sure that you have gotten the math part of what is happening here. Now the next part is basically going to be just the steps of Euclid and finding Bezoid coefficients. So I have 17 and 7. So that's what I got over here. Then 17 and 7, the quotient is 2, the remainder is 3. And if I now I'm not doing these steps over here, but I would like you to do the steps that are here, which is I would write now the remainder 3 in terms of 17 and 7. So I can write this as, we can write 3 is equal to 17 minus 2 times 7. Then we know that 7 can be expressed from this line over here. So we have 7 is equal to minus 249 times 17 plus 1 times 4240. We're going to substitute 7 over there, over in the first line over here. And that will give us the values that we are looking for. In this case, the value of s would be 499. The value of t would be minus 2. Again, a little bit of check. to know what the values of x times s plus y times t are. That will guarantee that the spreadsheet is doing it right. Again, you can check for the actual formula used in spreadsheet to see why the formula are being done the way they are. Continue. Eventually, we get the remainder to be 1, and that's good news because when we reach the remainder of 1, that means we know that the two numbers that we selected are relatively prime. Now, at this point, the value of S is minus 1247, the value of T is 5. So that means I can write 1 as 17 times minus 1247 plus 4240 times 5. So this is where we are going to find the value of GCD. GCD is, we're going to find the value of the Bezoid coefficient that we need for the private key. So in this case, the value of the private key is going to be minus 1247. I have selected this specific example because there is a possibility that the private key you get happens to be negative, in which case we need to uh, spend a little bit of time and do something else to find the actual private key because we want the actual private key to be positive. So let's focus on the interpretation of that. That's in the third sheet over here. So what we have here is we have found value of s and value of t such that s times e plus pi n times t, s times e plus pi n times t is 1. So that means I can write s dot e is equal to 1 plus minus t times phi of n. We are going to select S as our private key, and we have talked about why S is the private key in other modules, so I'm going to not go over this. We need S to be a positive integer, and for that T would have to be negative. Note that S and T both have to be integers. We are not allowed to have fractions to make this work. So what we're going to do is a very simple trick. We suppose I got the value of S to be negative. I'm going to first make this observation. What we got was S times E plus phi n times T was 1. I'm going to add phi n times T to both of them. So I get S times E plus phi n times T plus another phi n times, no, excuse me. I have S dot E. I'm adding phi n times T. Sorry, there was a typo on the slide, so I went ahead to fix that. Okay, so now I got this right. So I have S dot E, S times E plus phi n times T was 1. I'm going to add this phi n times E and subtract phi n times E. That's not going to change the value because I'm adding the same number and subtracting the same number. Now what I'm going to do is this. Look up here. I'm going to take this term S dot E. Then I'm going to combine this with this other term, and I observe that E is a common factor of those. So I'm going to write this as E times phi n plus S plus phi n times. So I'm going to take the remaining two numbers that I had, which were phi n times T, which is this number over here, and this number over here. And I'm going to take phi n as a common factor between them. So I got E times phi n plus S plus phi n times T minus E is equal to 1. Now, the reason we did that was because S was negative. When we add phi n to it, S will become positive, and T was positive, T minus E will be negative. What we wanted was the number that was multiplying E should be positive, and that's what we would get by doing this. Now, this is one of the places in the spreadsheet where you need to enter the data by hand. The spreadsheet isn't coded to do this automatically. You will have to do this, enter the old value of S. So you can see that I have entered it -1247. I have the value of E would be automatically gotten from the spreadsheet. And now the formula would, you also have to write the value of old T manually, and phi n would be gotten automatically. We will compute S and T. So we can also have some check in the spreadsheet to make sure that these values are actually correct. Okay, so we found the value of S, which is the private key. Now you need to go back to the choose prime sheet and enter this key by hand. This is something that is not done automatically. This is something you will need to enter yourself. Okay, so now we have the public key is 17, the private key is 2993, and so we can now use these to encrypt and decrypt. So in this case, for the encryption, the key is going to be the public key, so we are getting it from the first sheet. This needs to be always 2 if you're using it for RSA. If it this spreadsheet is also doing the work of converting number from one base to another, so you can use it standalone to convert a number to a different base, but for the purpose of RSA, this number has to be 2. We have a message that we are going to encrypt with. The value of n is gotten from the first sheet. The value of the private key, the value of the encryption key in this case is the public key, which in this case is 17. Okay, and that's why I have a note here that says the base must be set to 2 if you're using this for RSA cryptography. So what we're doing here is we're converting the number to binary. So it's 17, we divide by 2. So the quotient is 8, remainder is 1. Then again divide by 2, again divide by 2, again divide by 2. And essentially what is happening when we do this is basically 17 is now expressed as 2 to the power 0, because this is the first number that we're going to get, plus 2 to the power 4. So if you read the number backward, it will be 1, 0, 0, 0, 1. That is 17 in binary. Now, the right side of the sheet is going to do the same thing, but it's going to compute the powers. Remember, our goal is to find 36 to the power 17 mod 4387. 4387 is the value of n from the first sheet. So this is doing a little bit of what it is doing is on this column, it is just computing the powers of 2. So it's 2 to the power 0, that's 1, 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on. Here, we are going to compute the squares. So 36 is the original number. Now, to find the next number, we are going to take a square and take modulo n. So if you observe, this is what is happening. I'm squaring the number that is in the cell just before me and taking modulo with respect to n. I'm going to do the same thing next time. Square the previous number, take modulo with respect to n. Keep doing this. So this is basically going to compute 36 to the power 1, 36 to the power 2, 36 to the power 4, 36 to the power 8, 36 to the power 16, and so on and so forth. Now, the next part is figuring out which powers of 2 we should care for and which powers we shouldn't. So we should care for 36 to the power 1, and that's because I have a 1 here. So that's why I'm going to take the relevant powers. So if the number in this cell happens to be 1, I'm going to take the corresponding power. Otherwise, I'm going to ignore it and just keep the previous number. So in this case, I take 36. I do 36 to the power. Now I don't use 36 square because I don't need it. This bit, oops, sorry. This bit in the cell C14 is 0, so I don't need to take the second power. I don't take 36 to the power 4. I take 36 to the power 16 because 16 is needed for 16 is needed when I do binary split of 17. I needed to write 17 as 16 plus 1. I didn't use 8, 4, or 2, so I don't count those, but I will have to count I'll have to count 16 and 1. Note that you can use this sheet just by itself. So if I change this number, say to 25, sorry, let me just use it to 29, maybe. So in that case, 29 will be 16 plus 8 plus 4 plus 1. And in that case, the corresponding powers would be used in this case. Note that if you change this number on this sheet, that is going to potentially break the rest of the sheets because this number may not be copied back into the right places. So, but you are okay to do that if you just want to try out what this sheet is doing. Okay, so what we got is at the end of the day, the encrypted value is 3300. Now this last sheet is identical to the first one, except that we are going to use the private key to do the decryption. So in this case, this number is coming from the first sheet, choose primes. The rest of it is identical. I'm converting the number to binary, taking the relevant powers. So I'm computing 3600 to the power 1, to the power 2, to the power 4, to the power 8. And again, each time I'm computing this simply by squaring the previous term and taking modulo n. Keep doing, and at the end, we will find that the encrypted message, sorry, the decrypted message happens to be 36. Note that there are some numbers that you cannot encrypt with RSA with what we have learned. So there is a possibility that at some of these cases, you might come across it. Those cases are rare, and because those cases are sort of beyond the maths that we want to study right now, I'm not going to go through that. But if you come across those cases and you can't figure out why that is happening, you can come discuss it with me or Dr. Tong to go over that. Okay, this concludes this video. There is no worksheet for this, but we would be doing some of these problems in class. I'm sorry, I meant there is no review quiz for this, but we will be doing problems related to this in the class.